Welcome back, everyone. You're tuned in to another explainer from Forge College. So, in our last session, History of Reentrancy Attacks, we took a pretty wild trip back in time to look at the infamous DAO hack, right? It was a huge moment in Web3. But today, we're shifting gears. We're stepping out of the history books and diving straight into the engineering blueprints. Today's explainer is all about the core mechanics of reentrancy attacks. Think of it kind of like taking apart a really complex engine to see exactly where and why the gears slip. Because, well, we have to understand the mechanics clearly before we can even think about fixing the machine, right? Here's a quick look at our agenda for today. We'll start with the vulnerability blueprint. Then we'll break down the slow-motion heist. After that, we'll look at the state mutation window, explore 2 ways to defend against this, and wrap up with next steps and takeaways. All right, let's just get right into it.
Section 1, the vulnerability blueprint. We're looking at the fundamental building blocks here.
So, to really understand how a smart contract gets completely drained, we first need to isolate the core building blocks of the exploit. And honestly, it all boils down to 2 specific actions happening in the exact wrong order. The first piece of the puzzle is what we call an external call. In the EVM, the Ethereum virtual machine, an external call, like when you use the msg.sender.call function, is basically an operation that forwards gas and totally transfers execution control over to another smart contract. To put that into perspective in the real world, it's literally like temporarily handing the master keys to the bank vault over to a random customer so they can go get their safety deposit box. You are just blindly trusting them to give the keys back when they're done. Wild, right? But that's how it works.
Okay, the second concept to grasp is state mutation. This is just a fancy way of saying we're updating persistent variables in a contract. You know, like modifying a user's balance in an internal accounting ledger. It is the exact moment the math actually solidifies permanently on the blockchain. So if the external call is the physical act of handing the cash out of the vault, the state mutation is the bank teller actually crossing your name off the ledger with a pen to show, okay, yep, you've officially been paid. And bringing those 2 concepts together perfectly illustrates the fatal flaw we're looking for. In a vulnerable smart contract, the execution sequence goes exactly like this. Step 1 is the check. The contract verifies you actually have a balance. Cool. Step 2 is the interaction. The contract makes an external call to hand over the funds. And then step 3 is the effect. The contract finally updates its internal ledger to say you've withdrawn your money. Now, do you see the glaring problem here? It's kind of crazy when you look at it. The cash is literally handed out the front door before the internal ledger is ever updated.
Which brings us to Section 2, the slow motion heist. Let's trace the execution. Let's completely freeze time for a second and watch this exploit unfold frame by frame. Here is the logical timeline of the attack. Step 0 is our initial state. Let's say you, playing the role of the attacker, have 1 ether, and the bank contract has 10. Step 1, you call withdraw. The contract checks its ledger, sees your 1 ether, and happily approves the transaction. Step 2, the contract issues the external call to send you the money. But wait, suddenly control shifts to your malicious contract. Step 3, well, this is where the absolute magic of the attack happens. Instead of just taking the money and returning control like a good user, your malicious contract's fallback function instantly calls withdraw again. The EVM is basically like an overly obedient blindfolded teller. It has 0 overarching business context. So, moving to step 4, it checks the ledger again, but because the ledger hasn't been updated yet, since we're still stuck inside that recursive loop, the ledger still says you have 1 ether. So what does it do? It hands you another ether, and this just loops over and over and over until the bank's entire reserve is completely wiped out. Only then does the execution finally return to the original frame to update the ledger. Now, what's really fascinating here is the complete detachment from reality happening inside the contract's memory. Just look at this comparison right here. During the reentrancy, like while that recursive loop is just aggressively firing, the contract's actual ether balance drops immediately. It goes down to 9 ether, 8 ether, 7 ether. But look closely at the attacker's balance in the internal ledger. It just sits there at 1 ether, completely lagging behind the reality of the situation. The contract's internal mapping is totally oblivious to the fact that funds are just hemorrhaging out the door. All right, let's move into Section 3, the state mutation window. We are zooming in on the exploitable gap.
You see, this exploit doesn't just happen by magic. It lives right here. It's the window between a successful check and the completion of the corresponding state update. That physical gap in the code, the actual space between the contract declaring, yes, you have funds, and, Okay, your balance is now officially 0. That is exactly where the vulnerability lives. The attacker is simply taking their malicious recursive code, parking it right inside that gap, and hitting repeat. Which naturally leads us to the $1,000,000 or, perhaps millions of Ether question. How do we actually close this window? Well, before we answer that, I just want to mention that if you're enjoying breaking down these mechanics and you really want to master them, Forge College actually has some incredible advanced learning programs that dive super deep into hands-on smart contract auditing. It's an absolutely fantastic way to bridge the gap between just understanding an exploit conceptually and actively securing production code against it. But for right now, let's look at the solutions we have at our disposal. Section 4. 2 ways to defend. Let's talk about securing the contract. Now that we've properly diagnosed the illness, let's prescribe the cure. The first strategy is, honestly, surprisingly elegant. You just reorder the steps. Step 1 becomes the check. Verify the balance. Step 2 is the effect. You update that internal ledger to 0 immediately. And then step 3 is the interaction. You finally make the external call to send the funds out. So the absolute crucial point here is this. By updating the ledger before you hand over the cash, you completely ruin the heist. If the attacker tries to loop back in, the teller checks the ledger, sees a big fat 0 balance, and immediately kicks them out. Boom, problem solved. So how does this actually translate into specific technical options? Well, mitigation A is what we literally just discussed, checks, effects, interactions. Fundamentally, it's just a logic reordering. Mitigation B, on the other hand, is adding a reentrancy guard. Think of this like putting a physical, simple Boolean lock, also known as a mutex, right on the vault door itself. It basically yells at the EVM, hey, while someone is inside executing this function, the door is locked tight. Nobody else can enter, not even a recursive clone of the person already inside. But, as with everything in engineering, neither solution is a perfect silver bullet. Understanding the trade-offs here is totally key to being a great developer. Reordering your logic, that's mitigation A, is highly efficient and saves on gas, but it does alter how rollbacks happen if a transaction unexpectedly fails. Mutexes, mitigation B, are incredibly easy to implement, but they are localized to that specific contract. A mutex won't protect you if an attacker loops into a totally different contract in your protocol that shares the same vulnerable state. And that, my friends, is exactly why layered defenses are always the strongest approach. Moving right along to Section 5, next steps and takeaways. Let's do a quick core mechanical recap. Let's summarize the core mechanics we've uncovered today. Listen, if there's one singular habit you need to adopt as a smart contract auditor, it's this. You absolutely must trace execution at the EVM frame level. Don't just read the code line by line like a standard script. You have to read it exactly the way the EVM executes it. Identify your state checks versus your external calls, and seriously, permanently burn this absolute rule into your engineering mind. State changes must happen before external interactions, every single time. I really, really love this quote, and I want to leave it with you today to demystify the whole concept for good. Reentrancy is not magic, it is a specific ordering of checks, external calls, and delayed state updates. Once you strip away all the intimidation and the mystery of the hack, it's literally just out-of-order execution. It's a solvable math problem, and you now have the exact blueprint to solve it. Looking ahead in the Smart Contract Security course, up next we'll be exploring common attack vectors and patterns. We're going to take these precise tracing techniques we practiced today and apply them to complex, real-world scenarios. We'll be evaluating things like pull versus push payment models to see exactly how these mitigations hold up under pressure. I'll leave you with this final, provocative thought to take back to your own code. Are your state updates actually happening before your external calls? Really think about it. Audit your architecture and close that mutation window for good. Thank you so much for joining me today. Make sure to visit forge.college to learn more about this subject and explore our massive library of Web3 related topics. Stay secure, keep learning, and I'll catch you in the next explainer.